All right, hello everybody. This video is going over the second lesson of Unit 2, which is on intramolecular force and potential energy. Today you should understand that atoms or ions bond due to interactions between them. And the objective today is to represent the relationship between potential energy and the distance between atoms, which are based on factors that influence the interaction strength between the two atoms. This slide shows the difference between single, double, and triple covalent bonds. A single bond means two electrons are being shared, for example, in hydrogen gas. Hydrogen is in group 1, it only has one valence electron, which is pretty unstable. So in order to maintain stability, it will bond with another hydrogen atom. So there is one electron from each hydrogen atom, and they share those electrons in form of a bond. Same with double bonds, except you now have 4 electrons being shared. So let's say oxygen gas. Oxygen is also unstable by itself because it has 2 unpaired electrons having 6 valence electrons. So those 2 unpaired electrons get bonded with the 2 unpaired electrons in another oxygen atom. So that would have a double bond, which is a total of 4 electrons. And then with a triple bond, that is 6 shared electrons. So something like nitrogen gas. Nitrogen has 3 unbonded electrons, so each nitrogen atom is going to bond out those 3 electrons to another nitrogen atom, and that will give you a triple bond, which is 6 electrons. So in order to truly understand the reactivity of single versus double versus triple covalent bonds, you have to understand sigma and pi bonds. So in a single bond, there's only one sigma bond. In a double bond, there is one sigma and one pi bond. In a triple bond, there is one sigma and 2 pi bonds. Now, why is there only one sigma bond in each of these types of bonding? That's because a sigma bond is formed by a head-on overlap of orbitals. So it can only happen one time in each kind of bonding. And since it is a head-on overlap of orbitals, it's a very strong bond, which provides the backbone of the bonding. And that is why a single bond is generally less reactive than the other ones, because the sigma bond is relatively strong. Then we have our pi bonds. So our pi bonds are formed by sideways overlap of orbitals, and they are a lot more weaker than our sigma bonds, because they are more exposed, and therefore they are more reactive. So since double bonds have a pi bond, they are more reactive than our single bonds. And then since our triple bonds have 2 pi bonds, they are the most reactive of the 3 types of covalent bonding. And then just a side note, as you add those pi bonds, you are going to bring your atoms closer together, which is why as you increase your number of bonds, you're decreasing your length between the 2 atoms. So for example, if I was looking at a carbon-to-carbon bond and it only had a single bond, it would be further away than the 2 carbons with a double bond, which would be even further away than 2 carbons with a triple bond. So the triple bond would be the lowest amount of length or the shortest length, and the single bond would be the longest length. Continuing on with our talk of stability, I want to talk about formal charge. We use formal charge to identify the most stable Lewis structure for covalently bonded molecules. And in order to calculate formal charge, you first need to understand what an atom is supposed to look like in terms of bonding. So if we're talking about a group 14 element like carbon, which is very commonly used in AP chemistry, carbon has 4 valence electrons. So if it were to bond out and gain stability, it wants to bond out all 4 of these electrons to be stable. So it's going to have 4 bonds and no lone pairs. So when you were looking at carbon atoms and it doesn't look like that, you need to calculate the formal charge. Then with our group 15 elements like nitrogen, those have 5 valence electrons, which means in a perfect world, they have 1 lone pair and 3 bonds to become stable. So again, if you're looking at a nitrogen, it does not have a lone pair and 3 bonds. You need to calculate its formal charge. Then with our group 16 elements like oxygen, they have 6 valence electrons, which means they have 2 lone pairs and 2 bonds. So if you see like a triple bond and one lone pair on an oxygen, you need to calculate formal charge because that's not how it's supposed to bond. And then finally, with our group 17 elements like chlorine, those have 7 valence electrons, which means they will typically have 3 lone pairs and 1 bond. So now let's calculate formal charge of these molecules. So again, we are looking for things that are not bonding how they are supposed to, because if they're bonding how they're supposed to, we know their formal charge is going to be 0. For example, if you look at this carbon, it has 4 bonds. So 4 valence electrons minus 4 bonds equals 0. So you can assume that if it's bonding how it's supposed to, like we just went over, you do not have to calculate it. So let's look at the other carbon on this molecule that is clearly not bonding the way that it's supposed to. We have carbon with 4 valence electrons minus its 2 bonds minus its 2 non-bonded electrons gives us a formal charge of 0. So this molecule, even though it's not bonding how it's supposed to, does have an overall formal charge of 0. Now looking at the top middle molecule, the chlorine valence electrons are implied here. They just didn't put them there because they don't want you to focus on that. They want you to focus on the carbon. This carbon is the same as the last one, so each carbon atom has 4 valence electrons, minus its 2 bonds, minus its 2 non-bonded electrons, so this carbon has a formal charge of 0. Now moving on to the top right molecule, we are going to first look at this nitrogen. We know nitrogen typically wants 3 bonds and 1 lone pair, but it has 4 bonds. So nitrogen has 5 valence electrons, minus 4 bonds, and no non-bonded electrons. So that gives us a positive 1 formal charge. So we would put a positive right next to this nitrogen. Then looking at this aluminum is actually a metal, and you normally see metals bonded ionically, but in this case it is bonded covalently just because of the difference in electronegativity. So aluminum has 3 valence electrons, so it usually just wants to bond out 3 times, right? Well, this has 4 bonds, so we're going to calculate formal charge. Aluminum has 3 valence electrons minus the 4 bonds here gives us a -1. So this aluminum has a negative charge. So overall, this molecule has a charge of 0 because we have a positive 1 and a -1, which bounce out to 0. But the nitrogen and the aluminum atom both have a formal charge. Now looking at the bottom left molecule, we have that weird looking carbon there with 3 total bonds in 1 lone pair. So we need to calculate formal charge. We know carbon has 4 valence electrons minus its 3 bonds minus its 2 non-bonded electrons, which means we have a -1 charge. So we would just put a negative right next to that carbon. Then looking at the bottom middle one, we have everything looks in order except, actually everything looks in order. So the nitrogen has 3 bonds and 1 lone pair, and all the carbons have 4 bonds, so nothing has formal charge. And now moving on to the bottom right one, you can see our chlorines again are implying that they have those lone pairs. We're not looking at those. We are looking at the phosphorus and the oxygen. So oxygen's group 16. It's supposed to have 2 lone pairs and 2 bonds, but it does not. So we're going to calculate formal charge. So oxygen has 6 valence electrons minus these 6 non-bonded electrons minus 1 bond gives us a -1. So this oxygen has a -1 charge. And then looking at this phosphorus is in group 5, has 5 valence electrons. I'm sorry, it's in group 15 with 5 valence electrons minus its 4 bonds. So this has a +1 charge. So again, overall molecule has a charge of 0 just because they cancel out. Now, how do we use formal charge in order to make sure we are drawing the best possible Lewis structure? Well, let's look at that bottom right molecule and figure out how we would draw that to lower or minimize formal charge. Now, oxygen has an extra electron, and phosphorus wants an extra electron, right? Because it has a positive charge. So what we can do is we can move a lone pair from oxygen and make it a bond between oxygen and phosphorus. So now we have phosphorus in the middle with our 3 Cls. And then we have a double bonded oxygen with its 2 lone pairs. So now oxygen is bonding how we want it to, our chlorine atoms are bonding how we want it to, and phosphorus is not. So let's go ahead and calculate formal charge and see what we get. We know phosphorus has 5 valence electrons minus its 5 bonds, so that phosphorus has no formal charge. So this molecule is much more stable than this molecule because there is no formal charge on the atoms. In which Lewis structure does the central atom have a non-zero formal charge? So let's go ahead and practice drawing some of these Lewis structures. So first we have PCl3. We know phosphorus, since there's only one of them, probably going to be our centralized atom. So we're going to put that in the middle. And we know phosphorus is in group 5, which means it wants 3 bonds and 1 lone pair because it has 5 valence electrons. So 1, 2, 3, 4, 5. Now, in this molecule, it has 3 terminal atoms. Now, why do I call chlorine a terminal atom? Because chlorine only wants 1 bond. So since it only bonds out once, it's probably going to be on the outside of a molecule. So we're going to take each of these bonds and form it with chlorine. And since chlorine's group 17, it wants 3 bonds, 1 lone pair. And then we have all of the atoms in the molecule bonding how they want. So there is no formal charge on any of these atoms. So phosphorus, since it has a 0 formal charge, that would not be the answer to this question. Then moving on to B, whenever you see carbon, since it wants 4 bonds, it's most likely going to be in the middle of the molecule. So I'm always going to start with carbon. And again, it wants 4 bonds. So I'm going to go ahead and put those 4 valence electrons there. And we have 4 terminal atoms, 2 hydrogens and 2 chlorines. So I'm going to go ahead and bond out my chlorines. Remember, chlorine's group 17 wants 1 bond, 3 lone pairs. And then hydrogen only wants 1 bond because it only has 1 electron. So now everything is bonding the way it wants to, so there's going to be no formal charge. So since carbon has a 0 formal charge, this will also not be an answer. Then moving on to HCN. Again, whenever you see carbon, go ahead and just put that right in the middle because that's probably where it's going to be. Remember, carbon wants 4 bonds, but there's only 2 atoms attached to it. So either this is going to have formal charge or there's going to be a double or a triple bond in the molecule. So we know hydrogen only can make 1 bond because it only has 1 electron. So we're going to start there. Then we want to look at nitrogen. We remember that nitrogen has 5 valence electrons, right? So 1, 2, 3, 4, 5. It wants 3 bonds and 1 lone pair. Now, it doesn't mean it has to be 3 single bonds. It could also be a triple bond. So now nitrogen is bonding how it wants. Carbon is bonding how it wants because it has 4 bonds, and so is hydrogen. So there's 0 formal charge on this molecule. So this would also not be the right answer. Then we move on to our C2H4. So again, whenever you see carbon, start with that in the middle. We have 2 carbons. And then whenever you have a organic molecule like this, split the hydrogens between the carbons. So since we have 4 hydrogens, I'm going to put 2 on one carbon and 2 on the other carbon. So we know hydrogen can only have 1 bond, so let's start there. 1 bond, 1 bond, 1 bond, 1 bond. And carbon wants 4 total bonds. Each one already has 2, so we're going to put the 2 other ones in between. So now that would be a double bond there. Looking at these carbons, they both have 4 bonds, which means they have a formal charge of 0. So D would also not be the correct answer. And then finally, our last option is NH3. So I'm going to put nitrogen in the middle. Remember, nitrogen, looking up here, wants 3 bonds and 1 lone pair. And we have 3 terminal atoms. So I'm going to bond hydrogen to its 3 non-bonded electrons and then add its lone pair. So all of these molecules have a central atom with a formal charge of 0. So the answer for this would be F, none of the above. In which of the molecules below is the carbon-carbon distance the shortest? So when I'm talking about the shortest distance, remember, the more bonds you add, the tighter the pull between those 2 atoms. So I'm looking for the longest bond. In this case, if you look at B, there's a triple bond between those carbons, so that would be your answer. Then our next question says, as the number of covalent bonds between two atoms increase, the distance between the atoms blank and the strength of the bond blank. So as you increase the number of bonds, we know that you're going to decrease the length. So the distance between the atoms is going to decrease. So that means A is wrong and C is wrong. And then the strength, because there are more bonds there, is going to increase. So the answer for this one would be D. All right, so now we're going to use that information that we just learned about and talk about bond energy curves. So bond energy curves represent the energy of a bond as a function of the position of its nuclei. So the graph essentially shows how the energy of a bond changes as two atoms move closer or further apart. So on the x-axis of this graph, we have the distance between the two nuclei. And then on the y-axis, we have the potential energy of the system. So when atoms are too close, like at 37 picometers that you see there, here, when atoms are too close, the energy is very high because the nuclei and the electrons are going to repel each other. Now, as they move apart, the energy is going to drop until it reaches the most stable point, which is where our bond is. So here, our bond is going to occur at 74 picometers or at 436 kilojoules per mole for bond energy. So the lowest part of these curves is going to be where the bond is the most stable and where that covalent bond will actually exist. Then as those atoms move further and further apart, the energy is going to go back up towards zero because the atoms no longer attract each other strongly. So let's break all of that down separately just so that we can really understand these types of graphs because they are all over the AP chemistry exam. So when atoms are farther apart, like in that purple box on the screen, their potential energy is basically zero, which means there's pretty much no potential for them to bond, right? That's because they're not really feeling each other. The positive and negative between the proton and the nucleus and the electrons in the electron cloud, they're not attracted to each other because they're too far away. So there's no significant attraction or repulsion when they are too far away from each other. Then moving to the left on the curve, we have the atoms close enough to each other to where they're starting to feel that attraction, but not to the extent as a covalent bond is formed. So as those atoms move closer together, the attractive forces are starting to pull them in, which does lower the potential energy. And that drop in energy is just telling you that the atoms are starting to form that bond. Now moving to the lowest part of the curve, this is called the equilibrium bond length. So here, the attractive and repulsive forces balance each other out, which makes the bond very stable. So for this specific bond, the actual bond length is 74 picometers because we know at this point of the graph, it is the most stable, which is where the covalent bond will actually exist. And finally, the leftmost part of the graph. So this is where the instability comes in. Because these two nuclei are so close to each other, their electron clouds are overlapping and their nuclei are repelling each other. So the potential energy is super high and the bond is extremely unstable. So in terms of stability, this part of the graph is very unstable. This part of the graph is very stable. All right, so just going over all the different pieces of this diagram before we start doing some examples. Potential energy is the energy linked to attraction and repulsion between atoms. So in this specific graph, we can kind of think of a vertical line here. This would be repulsion, and this part of the graph would be attraction. So in here, right, they're so far away from each other that there is no attraction. But as they get closer to each other, they start attracting to each other. Then they get to this sweet spot of attraction and repulsion where they kind of balance each other out and it's a very stable bond. But then as soon as they pass that, they're getting too close to each other. Their potential energy goes very high and they want to get away from each other. So they're very reactive. The distance at which the two atoms have the lowest energy is where the bond is the most stable. So that's something that you really need to make sure you understand. At the lowest part of this graph, that is where the covalent bond is going to occur because that is where it is the most stable. And bond length is the physical distance between the two atoms bonded to one another. So if you were given a graph like this and you had to say, the bond length of the covalent bond when it's at its most stable point. In this case, it would be 74 picometers. And then the bond energy is the amount of energy required to break 1 mole of a specific bond. So we will get into this when we get into our later units. However, I'm just going to briefly explain it to you. The bond energy is the amount of energy to break a bond, right? In order to break a bond, you have to put energy in, which is why it's a positive number. So in order to break this bond, we have to put in 435 kilojoules per mole. If you're thinking about it in the other way, if you want to talk about how much energy is released when that bond is formed, when energy is released, it's negative. So if it was asking you how much energy is released when the bond is formed, that would be negative 435 kilojoules per mole. And then the higher the bond order, the shorter the bond length, and the deeper the energy well. So what do I mean by that? If this was a carbon-carbon bond that we're looking at, right? That means this is our point at which the carbon-to-carbon bond is the most stable. So that is our single carbon-to-carbon bond. Now, that is a bond order of 1 because it only has 1 bond. If we were to do a curve for bond order of 2 for carbon, which just means a double bond, that means that this is a shorter bond length, right? So if it's a shorter bond length, that means we need to move it to the left. It's also a higher energy in order to break it, which means it's going to have a deeper energy well. So not only is it going to be more to the left, it's going to be lower. So our curve would look something like this. See, we have a deeper well, which is telling us that it takes more energy to break the bond because it has 2 bonds. And it is more to the left because it has a shorter bond length because, again, more bonds, shorter length. And then a triple bond would be even more drastic than that. So triple bond or a bond order of 3 means we have an even shorter distance and an even deeper well. So it will be something like this. The following diagram shows the potential energy of 2 atoms as a function of internuclear distance. Which bond is the strongest? So first, let's look at that first question. Which bond is the strongest? Now, if a bond is more strong, right, it takes more energy to break. Since this is 0, and we know going down, we are increasing the amount of energy we need to break the bond. If it takes a longer distance to get to this green line, that means this is a higher bond energy. So which bond is the strongest? That would be the W to Z bond. Then which bond is the longest? Now remember, internuclear distance is the x-axis. So for our W to Z bond, the most stable point is here, but for our X to Y bond, our most stable point is here. So our longer distance is the XY bond, whereas the WZ bond would be a little bit shorter. Say the following image is a diagram of chlorine atoms bonded together. Where would bromine fall in comparison. So if you're looking at your periodic table, you should see that chlorine is higher up than bromine. And what that means is chlorine only has 3 energy levels, whereas bromine has 4 energy levels. Since it has more energy levels, the radius of bromine is much bigger than the radius of chlorine. So because bromine has that extra energy level, the distance between the two nuclei is going to be a lot larger than between the 2 nuclei of chlorine. Because of that, when we're drawing our bromine to bromine comparison, we know that the bottommost peak is definitely going to be to the right of whatever it is for chlorine. Now we need to look at energy. Looking at chlorine and bromine, they're the same type of molecule. However, let's think about it in terms of Coulomb's law. Now, bromine, its outermost electrons are a lot further from the nucleus than chlorine is. So because it's a larger atom and the pull of the nucleus is farther from the electrons of the other atom, it's going to be easier to remove. Since it's going to be easier to break, that means it will take less energy, which means our well will be a little more shallow. So not only do we have a more shallow of a curve, the curve also has to be moved to the right a little bit because it is a greater distance. So your curve would look something like this. So shallower well, which means less energy, and bigger distance,